Joining me to another section on integration by part, and in this section I'm going to take the two other ways to get through integration by part. The first one is applying integration by part one more time, so we call it repeated by part, repeated integration by part. Okay, so let's take one example to see where the repetition comes from. Example one, or the only example I have here. Yes, if I have to integrate a function as this, why do I use integration by part? Because I have two functions, ux vx, multiplying product of these two functions. Again, don't forget about this acronym, is going to help you. Do I have a log function? No. Do I have reciprocal? No. Do I have algebraic function? Yes. So it means I start from that, x squared. You know, exponential, there's exponential function, but it's at the latter end. Okay, so you don't even go there. We just end algebraic function x squared. It means the v is whatever is left here. Okay, and then the u now becomes 2x dx. And then if I want v, it means I'm integrating the function, which I'm supposed to get negative a negative x. I'm sure by now you know what integral of ax does. It's 1 over a EAS. I want to remind you of that. And since a is negative, that's what I have. Now let's do the substitution. So it means I have the integral. Probably I want to just set the entire slide down for you to just follow. We are taking slide 6. Alright. So integral u is x squared. dv is, where is the v? E negative x dx. This is actually whatever your initial problem was given. It would always result in your initial evaluation. The important things are this other part. U is x squared. V is, so I have negative here, e negative x minus integral v. V, where are you? Is 2 negative ex du was 2x dx. If you don't take time to pick these things right, you might not even to get to see the repetition. And so you want to be smart. Negative x squared e negative x minus, so plus, because I have two negative multiplying, plus integral. If I want to rewrite this to look nicely in mathematics form, that's what I have. So there's my integral. That this would have been the answer, let's say plus some constant of integration. This would have been my answer, but you realize that it's not well simplified. So I want to change the pen now. It is not well simplified because I still have integral found here. All the examples we've done previously, it was in a simplified form, and so this is where the repetition is repeated by part. If I want to simplify this, I have to go through another integration by part. So let's take that part. I have integral 2x e negative x dx. That's what I want to find, and that will be found on my slide, I think 7. So what do? Still, I'm going to use my acronym. I'll never forget this. Do I have a log function? No. Do I have reciprocal? No. Do I have algebraic? Yes. So it means my u is going to be 2x, and then the other part of the problem takes everything here. This means that the u, you're going to know, you're going to get 2 dx, and then this means that my v, integration, I have that. So there's a substitution. Integral of u dv is equal to uv minus integral v du. Okay, so integral u is 2x dv is negative e negative x. What have I missed? I think I've missed something. I always make wrong choices. So 2x e negative x dx, for that is equal to u. So these are these guys. U is 2x here, and then v, I have negative ax minus integral v is to negative ax du. The u is 2 dx. Okay, so this is the same as negative 2x e negative x. Because of this integral limit, I have plus. I can bring 2 out and say I'm going to integrate just this guy here. Now I can simply I can simply integrate this plus and I'm going to get negative now, so the plus still goes away. Negative 2e negative x plus some constant of integration. This is what my 2x e negative x dx gives me. I want to label that as equation 1b, and then here is going to be my 1a. So if I substitute this, so I have to substitute 1b into 1a. Okay, and then that is what you do. It means that the initial integration, which was s square e negative x dx, is equal to the first part of the equation we had was, let me scroll, I hate scrolling up and down of my work, this part of the work, negative x square ex negative s square e negative x plus everything here. So instead of plus, I have negative out. Okay, plus negative 2x plus c. Okay, from here you can simplify further. That means you expand and then group like terms, and that's it. That's just it. If I factorize negative x out, I'm going to have this minus 2x minus 2 plus c. You realize that in my preamble or in my slide, I'm trying to integrate this from 0 to 7. So sometimes the smart way, finish with the entire integration and then evaluate whatever you had with the element 0 to 7, or right from the start. Means here I would have evaluated from 0 to 7, 0 to 7, but I wouldn't want to do that. I want to finish with the entire integral and then do that evaluation. So that's how the repeated root is done. This to tell you that if you have the third repeated, assuming I integrated this, I still have the integral of some x ex. I have to do the integration by part over and over again till all other integrations vanishes. Okay. Let's see another interesting part, which is where we have reoccurring integrals. Reoccurring, as the name suggested, it means there's some kind of, it's a repetition, but we have something happening at the same time. We have some forms, a common form that we can simplify. So let's take the first example. I'm going to integrate ex sine x dx. Don't forget this acronym, please. Do I have a log function? No. Reciprocal? No. Algebraic? No. Do I have a trig function? Yes. I have a trig function, so it means I end there. Where is the trig function? Is here. Sine x. Even though we said your u should be simpler to differentiate and then your v should be simpler to integrate. So someone might say, let me take u to be this. It would work, but then there will be complications as you move along. So always go by this acronym. These are all the common functions we have. It means everything left here in the integration, these guys here, become my dv. So what do we get for du? If I differentiate sine, I have cos x dx. I always get confused with sine and cos. Let me check my answer here. Is negative or positive answer? It's positive. And then if I integrate this, I know I'm going to get ex. Okay, so that's your substitution. This means that my integral of u, which is sine x dx, is equal to u, which is sine x, v, which is ex, minus integral v, the same ex du, cos x dx. Okay, so let's see here. We have to now simplify further. There's the same as saying I have, before we simplify further, something happening, something interesting is happening here. This guy here, will still be under repeated. I'm loving this example already. This is repeated, so we must go through the repetition approach. Okay, so I want to change the pen to blue. I'm going to work out this part of the work. So with the blue part, my integral ex cos x must be done in some way. So uv minus integral u dv. What do you set your u to? You know, you always have the trick first. So my u be cos x, and then my dv becomes the remaining part of this. This means that u is not negative sine x, differentiation, and then v simply remains ex. So let's do a substitution. U is cos x, v is ex minus integral u is still cos x, and then dv. Where is dv? No, there's v du. So what is v? Ex. And then what is du? Du is negative sine x dx. Yeah, I think I forgot to add a dx to it. And so let's simplify this. So this is the same as cos x, or e cos, if I want to write it very well, it's going to be ex cos x plus integral ex sine x dx. Ooh, what are we saying? Someone might just get scared here, because you see that you have to apply under repeated integration by part. But when you get to the second stage of integration by part, you want to just pause. Okay, you want to pause, because I don't know how, if you keep integrating by part, you will still end up doing repetitions all over again. So pause. Let's do substitution first. Initially we were looking at ex sine x dx. Let's do a substitution. So this is 1b. We want to substitute into 1a. So I have ex sine x, ex sine x plus, was it plus or minus? What did we get for initial thing? It was minus. Okay, so let's quickly do that. Let me clean the plus. It's minus, and then let's substitute the first integration by parts we did. We had ex cos x plus, let me do this thing more. So everything here, 1b part, we have ex cos x minus integral ex sine x dx. That's what we had. Okay, so let me just cater for the operations. Minus ex cos x, this guy and this guy gives me plus integral ex sine x dx. Can you tell me what is happening here? I'll be changing the pens to make it easier for us to visualize things. So blue, ex sine x dx. What can you tell from here? You realize that this is the same as that, and this is where the recurrence happens. So I have to take it to the other side of the equation. It's going to be twice of it. I think I've messed up, sorry for that language, but my operation, this is where it gets so frustrating, because if I take it to the end, I'm going to get 0. If I take positive here to the other part, I'm going to get 0, which is not supposed to be so. So what did I miss? What did I miss? Here was plus, because 1b, so minus 1b is plus. So if I extend, it means it's going to be minus instead of plus. Please forgive me, take your time and go through this signs very well. So now I can take it to that and then get twice of it being equated to whatever is left here. I can factorize ex out and say this is sine x minus cos x. Okay, Now because my interest is in this guy, it means I simply have to divide through by 2, and that is my answer at the end of the day, plus some constant of integration. And that's how the repetition, no, there's a recurrence approach works. As simple as that. It wasn't difficult, was it? No. I think I have a trial one for you. Try this out. There's going to end up going through repetition and then recurrence. So take your time and then ensure you have these two playing interchangeably. Now I know you've been wondering where is the problem of the day, and I call it story time. In this story time, we have two problems. Okay, we are looking at electricity energy usage in a home, where it's been given per day as this function. T is in hours. Okay, with the hours given as 0 to 24 hours in a day. This is realistic. We can't have more than 24 hours in a day. The question is, how many kilowatts does this family use in the first 4 hours of the day? What do you think is happening? What do you think is happening? So I'll help you have a clue to it. First 4 hours of the day means I'm looking at 0 to 4. 0 means at time 0, and then of kt dt. Well, now my kt I know is 10 t e negative t dt. Are you going to apply integration by part or substitution? This will only when you work by integration by part. Then you can move to the second one. It is how many kilowatts does a family use in the first 4 hours of the day? Well, I think I've repeated the question here, so it's the same thing. When you are done, you are going to get a numeric answer because we have limits of integration attached. In the previous examples, it was indefinite, but now we have a definite integral. So how many hours or how many kilowatts per hour consumption is this? You get your answer. The second problem of the day has to do with drug dosage. It says suppose you are taking a drug through the mouth orally, it goes to the body and then there's some excretion through as urine. You know, we can also have sweat as excretion. It goes on to say that the total amount of drug that passes through your body is given by some integral summation, accumulation. So don't forget, integration is simply accumulation over time. That's why I say area of a something. Alright, so there's the same as summation or accumulation over time. And then the function itself is given by this preamble where k is greater than 0. Okay, find a formula for that. So it means just evaluate your function, and when you are done, estimate at the limit 0 to 1. Let me correct myself here. After finding integration of et dt 0 to big T, it says now try and evaluate the same guy at 0 to 1, where k, now your big T is equal to 1 and then your k is 0.2. It means at this stage you're going to still have variables of capital T and k within, but when you come to the second part, now you're going to have a numeric because some values have been given. So k is a decomposing, which one should I use? How the drug breaks down with respect to time. Okay, and that is it for our integration by part. On this note, we come to the end of our integration, and as our life as human beings, we can attribute our lives to integration and derivatives. My life is the accumulation of my happiness over time between the day I was given birth to the time I die, and that's how beautiful integration is. And so I hope my calculus series has been so interesting for you. You can go over the lecture videos over and over again and then try and solve all the problems of the day given. I'm your tutor, Reda Lacey Egan. I'm with the Maths Department, KNUST. Don't forget, if you've not subscribed yet, you know what to do. Let's keep subscribing and then let's have fun with our mathematics. Bye bye.